In the last lecture, we had a logical view of the file systems. In this lecture, we'll see how a file system is implemented. As we said in the last lecture, that our implementation will mainly be based on secondary storage device. That means a magnetic disk. Okay. Therefore, before we start the discussion, let us revisit the structure of a magnetic disk and its properties. I hope you will remember this plate where I have shown schematically a magnetic disk, right? As I said that the magnetic disk consists of several tracks. Okay, here is a track, right? And each track, say, is divided into, so to say, a sector. For example, this is a sector, right? And the minimum amount of information, right, that can be read from or written into is a sector. The sector is generally half a kilobyte in size. That means it is of the order of 512 bytes, right? Now, a magnetic disk, as this plate shows, which I showed earlier also, can have many platters like this. Okay. Okay, this is a platter, one side of that platter. Okay. Here you see that I have shown 3 platters, right? And the disk is rotating at a very high speed. Okay, of the rotation speed can be 3,600 to 7,200 RPM. Here are the read-write heads which can move forward and backward. Therefore, the read-write head just moves over the surface of a platter, say like this. Okay, and as it moves either forward or backward, it moves from track to track. Okay, and since the disk is rotating at a very high speed, say here is a drive motor, the disk is rotating at a very high speed. If the track is here and the disk is rotating this direction, the sector will sometime will come under the read head, okay, and that sector will be read. Okay, therefore you can see that amongst the different characteristics the magnetic disk should have, that we should be able to tell, we should have that how many platters are there and therefore how many surfaces are there and what are the information content of it and at what speed the disk rotates, etc. Now, I have given certain characteristics of a magnetic disk, which I also gave earlier. Okay, the typical figures I gave earlier also. The number of platters is generally 10 to 15. Okay, for example, this number of platters are 10 to 15. Number of recordable surfaces are therefore 20 to 30, because each platter you can write at the top surface or on the bottom surface of it. The speed of rotation can be 3,600 to 7,200 RPM, the speed of rotations of this platter. And this is very important, speed of rotation, because depending upon this speed of rotation, okay, the access time will depend, right? How it depends, we'll come to, okay? Now, the tracks per surface are generally the tune of a typical figure is 5,000 to 6,000. Sectors per track is 64 to 200. A typical figure is 150. A typical sector size, as I said, is 512 bytes. The track numbers are generally written at the beginning of a track. The sector numbers are written at the beginning of a sector. And CRCC, okay, that error detection and correction code, cyclic redundancy check code, is written at the end of a sector. Okay. Now let's see. When you say a cylinder consists of all the tracks in the same relative position of a surface. Okay, for example, say track number, say 5 of this surface, track number 5 of this surface, track number 5 of this surface, track number 5 of this surface. and the track number 5 of this surface and track number 5 of this surface, all these track number 5s will constitute the cylinder number 5. Okay. Therefore, we tell a cylinder that it consists of all the tracks of the same relative positions of the surfaces. Now, the most important thing why we recapitulated that entire characteristics of a disk, magnetic disk, is this, that we want to have some idea about the access time. And access time will depend upon the surface selection time. That means, for example, a particular information is there somewhere in this sector. Okay, to get that information, so we'll have to read the sector. To read the sector, we'll have to see that how much time we need to read the sector. Okay, and for that, firstly, that what we'll have to do is that we'll have to select the surface on which the sector is. That is a bit negligible, okay, since electronic switching is involved. Okay, when I say it's negligible in comparison to other timings, as we are coming to. The seek time is a time to move to the target track, and naturally it will be depend on the start track. For example, say if somebody was here, by somebody I mean the head was here, then if you want to come to, if you want to read some informations in this sector, therefore the head has to move, okay, from this track to this track, and this time will depend upon where the initial starting track the head was on. For example, it was here, then it will take more time to come over to this track, but if it is in the next track, it will take much less time to come over to here, okay, to the desired track, right? And therefore, we say that it depends on the start track from where it starts, and the average is around 8 millisecond to 20 millisecond, depending upon the disk drive. Naturally, will vary from application to application due to locality of accesses. By that, I mean, for example, since some application is asking data which is on, so for example, this track, and the head is already there, you know that immediately the seek time will be much less, okay, and therefore, you see that, but the application, you see that it depends on the application. But if the application is such that one data is here, another data is here, and the other data is here, then the head has to move, okay, quite randomly, and therefore the seek time will be much more, and therefore the access time will be much more, okay. The average seek time, as I said, that it is from 8 millisecond to 20 millisecond. The third important characteristic, okay, is the rotational latency. Okay, let L be the average rotational latency. As I said earlier when I was discussing magnetic disk, the rotational latency is that after you have the head has come to the track, the time it takes for the designated sector to come under the read head, okay, is called the rotational latency. Sometimes it's called the search time also, okay. Therefore, you see the rotational latency will depend upon the speed at which this disk is rotating, okay, and that is why a high-speed disk is always preferable. Now, the average rotational latency will be half, okay, the time of one revolution, because you know that your disk may be, your sector may be right, okay, right almost under the read head, or it can be just as meet the read head, okay, and has to give a complete rotation before it comes to the under the read head. Therefore, we have taken it to be half the time of the rotation of the entire disk, and if it is a 3600 RPM is the disk speed, then the rotational latency is 8.33 millisecond, and if the speed is 7200 RPM, then the rotational latency will be 4.17 millisecond. Therefore, higher the speed, naturally the rotational latency is lower. Okay, that is why the designer chooses small diameter disk. Okay, because this can rotate at higher speed with lower power. It needs lower power and can rotate at higher speed, and therefore the rotational latency is much less. Okay. And next comes the data transfer rate. Okay, the data transfer rate depends on the sector size. That means how much data is there in the sector, in one sector. Rotational speed, because okay, as the disk moves, the data is read and is passed on. Okay, it's transferred, and naturally the recording density, and the typical range is 10 to 15 megabyte per second. Now the mid-range and high-end disk controllers have cache, okay, in the controller itself, which can store several sectors, and in that case the transfer rate increases and the typical figure may be 20 to 40 megabyte. By that I mean is this. So example, so what can be done is that as the sector is passing through the read head, the data is read and transmitted. Okay. Another is that let the data be read, kept in cache, and you see in that case the data can be read earlier and the transferred at a much higher speed, okay, from the cache, okay, and in that case the transfer rate turns out to be much higher, say 20 to 40 megabyte per second is a typical figure. Now all this is for what we want to have is a read time. Let us see, because we'll have to read or from the disk or write into the disk, okay, to have any information retrieved or written into. Therefore, the time is important, and let us try to have an estimate of the read time. The read time we have calculated, assuming that the sector size is 512 byte, rotation per minute is 7,200, average seek time is 12 millisecond, transfer rate assumed to be 20 megabit per second, and the controller overhead is 2 millisecond. Okay, this is an overhead of the controller, okay, to stabilize and start operation. All right. Then the read time will be head positioning time to, if we know which sector it is, naturally we have to know that which particular sector my data is before we can read at all. Therefore, it will be head positioning time plus transfer time. The head positioning time naturally consists of seek time, the rotational latency plus overhead plus transfer time. Now, taking all these figures, seek time is 12 millisecond, rotational latency is 4.17 millisecond, then overhead is 2 millisecond, all taken together turns out to be 18.17 millisecond plus the transfer time. Okay. Now, the transfer time therefore will be 18.17 millisecond, 18.17 millisecond plus the data transfer time. If we transfer one sector, then this will be the transfer time for one sector, say 512 byte, and the rate is 20 megabyte per second. Therefore, it will take 0.025 millisecond. For two sectors, it will be double, 0.05 millisecond. Plus four sectors, it will be 0.1 millisecond only. Therefore, you can see the transfer time is very, very low, okay, almost negligible with respect to that, you see the head positioning time, which is 18.17 millisecond, right? Therefore, you can see it is always economical and advantageous that once that head is positioned, right, it's better to read more than one sector than simply read one sector, because you know that additional time will need, okay, from one sector to four sector is only from 0.025 to 0.10 millisecond, which is quite negligible with respect to this time, right? That is why instead of, whenever a disk read is taken, okay, instead of transferring a simple one sector, simply in one sector, several sectors are blocked together and that entire block is transferred, okay? Say two sectors or four sectors are transferred together, okay? Because that does not take much amount of time once head is positioned. This leads to what we call the blocking and buffering. Let us see what we mean by blocking and buffering. by blocking and buffering, we mean that, say, a physical record. Okay, let's define what we mean by physical record. The physical record is the unit of information actually read from or written into disk. It may be 1 sector, 2 sector, or 4 sector. Therefore, if we say that the physical record is 4 sectors long, okay, then we assume that the 4 sectors are being read or written into simultaneously. Now, one thing is that whatever I talked about the read time naturally will be equivalently valid for the write time as well. Okay. And by logical record, we mean that a collection of records, okay, that means a collection of fields of the records treated as a unit from the user's standpoint. Okay. Therefore, this is our logical record as users views it, and the physical record as a system, okay, as a block of information reads from the secondary storage or writes into the secondary storage. And we define now few terms which we'll be using. Say, when each physical record contains exactly one logical record, the file is said to consist of unblocked records. Okay. One logical record, say that unblocked records the file consists of. Now, if that physical record contains several logical records, file is said to consist of blocked records. In this case, that for fixed length records, if our logical records are of fixed lengths, block contains integral multiple of records, and we say that to be a blocking factor. Okay. When that logical records are of fixed length, but if it's of variable length, the logical records are of variable length, the records may vary in size up to a block size. Generally, that is what is permitted. Okay, the logical record size is not allowed to be more than the physical record size. In that case, management problems transfer to be more severe. Therefore, generally, if it's a variable length records, okay, the logical record is allowed to vary in size up to the physical block size. Okay. Therefore, these are the terms that we'll use in the subsequent discussions that we are going to have. Okay. Now, second point is the buffering. Now, see, for example, if somebody is asking a particular record, okay, from logical record from the file system. Now, that record, to fetch that record, a good amount of activity is involved, as I said, okay, and the block will be read, and from there, the particular record will be given to the user. For example, that user's record may be only of, say, 20 or 30 byte, but for that, naturally, the head positions will be done. That entire physical block will be read, which may be of 1 or 2 kilobyte, and that particular 20 byte will be selected from that 2 kilobyte and will be given to the user. Now, the situation may easily be that the user is going for sequential access, which means therefore immediately the next logical record the user will ask for. And for that, if the entire procedure has to be repeated, then it is an unnecessarily wastage of time. And that is why what is done is that whenever a block is read, okay, it is kept in the main memory, okay? And before the file systems goes to search for a particular logical record of an user when it's requested, it first sees whether the corresponding physical block is already in the memory, and if it is there, the logical record can be taken from there and given to the user. Similarly is the situation for writing. Then when you write it, you first write into a buffer in the main memory, and when the buffer is full, and the buffer is the size of the physical record, then that buffer is transferred into the secondary storage. Okay, that way you can see that a considerable speed, and efficiency can be incorporated into the read-write procedure. And that is why the second important factor is called the buffering. Here, buffers in the main memory are kept to hold the blocks of records, and we call it a buffer cache. Now the thing is that before a user wants to use a file, he opens it. The moment it opens, the buffer is created for that particular file, and you can have a buffer per file. Sometimes we have sometimes not, more or less it is generally used that double buffering is used. Okay, that when one buffer is being used, the second buffer is filled in. Okay, that is why we call it a double buffering. But more frequently what is used is a buffer pool, which means the system keeps a pool of buffers to be shared amongst all the files that has been opened. Okay, in that way, you see that if you keep a pool of buffer, we'll have to keep track of which particular buffer is being used by which particular file. And if we keep this information, right, in that case, that buffer can be used very efficiently, very effectively to have efficient reading and writing from the file or into the file. Okay, and at the same time, if many users are sharing files, okay, then also that buffer pool will be quite advantageous. Now let us see that when file systems are implemented, how records are fetched or written into. Generally, I have given here a, so to say, a modular structure of the system for reading from or writing into a file. Okay, this consists of, say, submodules or logical file systems to which, say, the request to read a particular logical record is given. The logical file systems checks the protection and security, that whether the permission, whether the access that is requested is permitted or not. If so, then the logical address is passed on to the physical file system. The physical file system takes the blocking factor into consideration and then determines which physical block address this particular logical record is existing. Because you see that a file naturally will consist of many records, and therefore it will be blocked into many physical records, and these physical records will be kept in the secondary storage. And therefore, if you have to access a particular record, you'll have to find out which particular physical block or physical record, okay, that this logical record contains, and that is found out by the physical file system. Once you have the physical block address, check that whether that physical block is in the cache or not. If it's in the cache, naturally you retrieve the record and return. Almost no time is needed, okay, very little time is needed. But if it's not in the cache, then the basic file system is invoked, okay, which maps the physical block address into the physical disk address. That means it now maps the physical block into the sector number, surface number, track number, sector number, okay, in the magnetic disk, okay, and the device drivers are invoked, okay, are invoked to the IO requests are issued, and that particular sector is read, and then only that, but not only that particular sector, that particular block is read, and then only that that record is retrieved from there and given to the user. So from this, okay, the module, right, what has been done is, as if that entire disk surface, I've assumed here that entire disk surface or the entire disk space is divided into the physical blocks. Okay, it may be that each physical block may be 2 sectors long, each physical block may be 4 sectors long, but the entire disk surface is now divided into physical blocks, and each physical block is given a number, unique number. Okay, therefore that unique number tells that what is the starting address of the sector of a particular physical block, right? and therefore that unique number can be mapped into a surface, a track, and a sector number. Okay, that is exactly what is done when a physical block address is found where that logical record is, and that is mapped into the physical disk address. Okay, by physical disk address means the surface, track, and the sector address. Now that is the basic file systems I/O operation that has been shown by means of this diagram. Let us now come to that allocation methods. By allocation method, we mean now that we have decided, okay, or we have taken that action that entire this surface has been broken down into physical block addresses, right? How a particular file is allocated space in a disk space, okay, in the disk space in terms of these physical blocks. That is our allocation method. Okay, for example, let us see in this plate that say this is the entire disk surface shown. Here are the physical blocks, right? Say we have numbered them as 0, 1, 2, 3. Assume that this disk space is small. We have only 32 physical blocks. And when we have, say that we have a directory of files or directories, okay, subdirectories. Say this is the directory. It consists of 3 entries as has been shown. One is a letter, which is a file. This particular attribute says it's a file. Its length is 03. By 03 means that its length is of 3 physical blocks, right? And the start address is 05, and we are talking here contiguous allocation. That means this particular file starts at the 5th block and has contiguously allocated 3 physical blocks, 5, 6, and 7. Okay, and this is our letter. Math is a directory, and it is allocated only 1 physical block, and that physical block is 13 itself being a directory. So FE, right, is once more a file which is of length 4, and the start address is 27. That means it starts at 27, and it's a contiguous allocation. Therefore, it takes 27, 28, 29, and 30. That size is shown here. That's a contiguous allocation for a file or a subdirectory in the disk space in terms of physical blocks. Right? Now let's see what are the disadvantages of it. Naturally, the disadvantage is growth of files is difficult. So, for example, if we want that this file should grow, and if we find that say block number 8, 9, and 10 are all occupied, okay, by have been allocated to some other file, then this file later cannot grow anymore. Okay, therefore a good amount of task is involved if we want to make this file grow. Possibly it has to be shifted to some other vacant place, and then only it can be extended. Okay. Another is the problem of holes. As had happened, I hope you remember that your partition memory management scheme, when you say that holes may be generated within the physical memory, which I should say that results into a good amount of memory being wasted. Here also, for example, such holes may be generated. For example, a file is allocated, several files, and in between there are blocks which is small enough, okay, which is too small that it cannot be allocated to a file. But if we take all the holes together, possibly it could be, it could accommodate many files, okay, many different files. That problem of holes is there, and compaction in the case of a secondary storage is very time consuming, and therefore is very costly, and therefore it's not generally attempted. Therefore the problem of holes one has to live with, okay, until unless one is willing to pay sufficiently for compaction. But the advantage is the random access, naturally. For example, if you want any particular logical record at random, you can very easily find out which physical record it is, which physical block it is, and you can access it. Okay. Now say, for that, let's see, how do I map from the logical address to a physical address? Okay, the logical, by logical address, I mean here that byte offset from the beginning of the file. Okay, that particular byte offset of that record from the beginning of the file. And by physical address, we mean that which particular physical block that byte will be there, I mean that record will be there. What we do is that here we have assumed that the block size is 1K, 1 kilobyte, all right? Now, let us take that logical address and find the quotient by dividing by the block size and find the remainder also, okay? Now, if we find the quotient and the remainder, it is easy to see that the physical block to be accessed for accessing this logical record, having this logical address, is Q plus the start block number. So, for example, if it is Q, is the start block number, say the start block number is 5 and the quotient is 2, then we know that we'll have to, quotient is 1, then we know that we'll have to go to the next block, 5 plus 1, the 6th block, where that logical record will be there. That is why we say that the physical block will have to access to find the logical record is Q plus the start block number, okay? And the particular logical record will be at a displacement of R, which is the remainder, okay, when you take the modulo operation, that displacement within that particular physical block will be R, okay, which means if the displacement is 10, then it will be 10th byte from the beginning of this physical block. Let me say once more, just to say that, for say this is 1 and this is a 10, right? Which means you'll have to go to the next block, start to, we'll have to go to the next block, which is 6th, and we have to go to the 10th byte, okay, from in this physical block to access this logical record, okay. Therefore, that is why I say that random access is possible. Now, the second option of allocation that we go for to circumvent the problem of that holes is the linked allocation. In the case of a linked allocation, what we do is this, that directory has two entries over here, one say the start and the other say the end, and the physical blocks that are allocated to the file or the subdirectory are all linked, okay, as a linked list. For example, see the file later will start at 1, therefore we'll have to go to the first block. It now says that it contains the part of the file, and since the file is of length more than one physical block, it says that you'll have to go to 14th block, okay, for the rest of it, right? Now, which means that this 14th block, okay, has been kept as an entry here, keep making it a linked list, okay? We go to first block, then take this entry, that 14th, go to the second block here, which is the 14th block, then that is linked to 21st block, we come to the 21st block here, that 21st block is linked to 12th block, okay, that 12th block is linked to the 6th block, okay, and that 6th block is linked to the 8th block, and that is the end of it, and therefore the link is -1. Therefore, it's just like a linked list. The blocks are kept in a linked list, okay. The start is here and the end is here, and end is maybe marked with a particular flag, say like -1. Okay. For example, this is for the file which consists of, say, how many blocks? 1, 2, 3, 4, 5, 6 blocks. All 6 blocks are linked together in and beginning and end of this linked list. This information is kept in the entry for that particular file. So mass is a directory and possibly need only one block, and therefore say the beginning and end, both of them marked to the same physical block. This is our linked allocation, and in the case of a linked allocation, you can see immediately the advantage we get is that growth is easily supported and we don't have to have any wastage of space. No holes are created at all. Okay, every physical block can be kept track of, whether it is occupied or unoccupied, and can be allocated when files or subdirectories are created, and deallocated, okay, when files or subdirectories are deleted. And the bitmap technique, that means 1 bit for every physical block, and that bit being 0 if it is not allocated, and 1 if it is allocated, can be used to keep track of the occupancy of these physical blocks, right? But the problem is that we cannot have the random access. The situation, let us see here, okay? Situation turns out to be that, say the logical address is given, how do I find the which block that logical address belongs? That means the record, logical record belongs. Once more divide it to get the quotient and take the modulo operation to get the remainder. Now the block to be accessed is a qth block in the linked list, which means that if it is, say, division tells me that the value is 5, then you have to start from here, okay, and go to the 5th block to get that logical address. That means start from here. This is the for example, by, say this is Q LA by B, logical address by the block size is 4. That means starting from the starting block, we'll have to go to the 4th block. This is the 0th block, this is the 1st block, 2nd block, 3rd block, and the 4th block. Here only we'll find the logical address, okay, and therefore here only we'll find the logical record in this physical block. And you can see easily that I'll have to traverse, one has to traverse all these blocks one after the other to get the link addresses till you come to the 4th block in the link, and where you can find the logical record, okay. And as such, that is why saying that block to be accessed will be the qth block in the linked list, and the displacement after you find the kth block will be R. That means once you have come over to, so for example here, you can go to the rth displacement to find that logical record. And you can see, because our access strategy will be like this, okay, we cannot have a random access. For example, if a record, logical record number is given, we cannot straight go to a particular physical block and find out that logical record, okay. We'll have to determine that which particular physical block it is, physical block number it is, and then we'll have to follow the chain of this, of that linked list to come to that physical block, and only after we come to that physical block, the displacement will give you the address of that logical record in that physical block, okay. That is the disadvantage of a linked allocation. And therefore, let us see that what we can do to circumvent this linked allocation, but at the same time, okay, we can avoid the problem of contiguous allocation, that is the problem of holes, okay. Such an allocation is the indexed allocation shown in this diagram. Here you see that this is the directory, this is the file. This file contains what we call an index block, right? This index block the block number, physical block number 13, contains the addresses of the physical blocks where the file has been kept. For example, this physical block 13 has been expanded here. It has, say, 1, 2, 3, 4 entries. -1 stands for, I should say, the null pointer. This means the logical block 0 of the file later is in the physical block 21. That means this is a mapping that has been done. So is for the other logical blocks of the file later. They are respectively in 7, 25, and 4, as has been mapped from the block 13 to 7, 25, and 4. -1 means is a null pointer, therefore this particular file later consists of 4 blocks. Now you see, under such a situation, what should be the mapping, right? Now once more, what we do is that we compute out the quotient and the remainder as is being done, B being the block size and LA being the logical address. Okay. Now in that case, the Q will give the displacement in the index block, which will be pointing to the physical block where that particular logical address will exist. That means the logical record will exist, and R will be giving the displacement in the target block. For example, if Q is 1 and R is, say, 10, in that case it essentially means that in the physical block 7, since Q is 1, it will be mapping to 7 at an offset of 10 from the beginning of the physical block 7. The logical record having the logical address will be found. Okay, therefore this is a mapping that will be used in this case. Now, what is the advantage of it? Advantage is naturally the random access. We can get a random access over here. But the disadvantage is that overhead of the index block has to be incurred, okay, for this kind of mapping, right? Now, one important thing now let us address, that if the file is huge, then what do I do? Two things can be done. One is that we make a linked list of blocks of index tables. That means we make a linked list of index blocks. Okay, that means that this index block, there will be more than one index blocks like this, and they will be chained. Okay, this is one way that it can be solved. Another is that we use two-level indexing, as has been done in this diagram. Okay, here you see the file is mat. Okay, the two-level indexing has been used. This is the outer index. The mat first points to the outer index from the directory, and every entry here in that outer index is a pointer to an index table, which every entry of which is now point to the physical block where the file has been distributed over. Okay, for example, this is a physical block 1 of the file, which is pointed to by this index block first entry, and this index block, okay, that index table is pointed to by the outer first entry of that outer index over here. In that case, you can see immediately that quite a huge amount of size file can be accommodated, right? Now, just to have a computation, if we assume that the block size is 1 kilobyte, okay, and the each block address is 4 byte, then it is can immediately see that the index block will have 256 entries, 1K by 4, right? So the file size will be 256 into 256 into 1K. That is the maximum file size we can accommodate. That means 64 megabyte. You see, this is 256 into 256, okay, right, into 1K, okay. That is the total file size that can be addressed by means of a single entry of the directory. Okay. Now, this is overall the way that the file system, physical file system, is handled. One important thing I think I should clarify here, and that is that so far as the logical view of the file system is concerned, we have treated the directories and the files to be separate, okay, as separate entities, right? But while implementing it, right, both the directories and the files can be treated uniformly. That means directories can be treated as files and can be implemented as files, okay, only while treating or reading from the directory, it has to be interpreted that way. Okay, therefore, that an uniform methodology of implementation can be used both for the directory as well as for the files. Okay. Now, before we end our discussion on the file systems, let us just give some case study report on Unix files. Okay, it says that 80% of the accesses are to files with size less than 10 kilobyte. Okay, which means not that users do want to keep or do keep two huge files, right? 90% of the accesses are sequential in nature, right? And of all the accesses, the 67% are reads, 27% are writes, and 6% are read, modify, write case. Okay. Now that can be useful while one designs a physical file system, okay, and the mapping that one implements. Now, let me in short give that what is the basic way that the Unix files are kept. Unix files and Unix directories are kept as inode, that means index node. One index node is either a directory or a file, right? For example, an Unix node has been shown here in the pink. An inode has been shown here, that index node has been shown here as a pink. This index node contains this information, that who is the owner, who is the group, what is the type of the file, right? What's the permission that is given, when it is last accessed, when it is last modified, okay, when the inode itself has been last modified, the number of links to this inode from the various directories, and the size of the file, right? Then comes the entries, okay, which point to the actual content of the file, right? Remember one thing, that this particular inode, an inode or index node itself is contained in one physical block. This points to the physical blocks where the file or the directory is kept, and this is a combined scheme that has been implemented, right? The first 10 entries are pointed directly to the physical blocks where the files have been kept. For example, direct 0 points to this physical block where the first portion, okay, of the file is there, and so on till it is the direct 9. Then it goes to single level indirection. That means this now point to an index table, which now point to the physical blocks where the portions of the files are kept. Okay, single level indirection. Here it is double indirection. That means it points to an index block, outer index say, then it points to another index table which points to the physical blocks. And here it is 3-level indexing that has been used. First level indexing, second level indexing, and third level indexing. When you had been talking about that indexed, okay, that indexing technique, instead of 2-level, naturally that can be generalized to more than 2-level, only that overhead of consulting that index table increases. Here, it has been done if the file size turns out to be, okay, gradually more. You know, up to this, up to, for example, the 10th entry, this is direct pointer. After that, the indirect pointer starts. Therefore, as the file size increases, okay, the consultation time for the later on physical blocks also increases, right? To remind you once more that this, therefore, that index node, inode, is itself contained in a physical block, and every inode either represent a file or a directory. That is the Unix file systems with the basic structure of it. And that's all so far as file systems are concerned. And we stop the discussion on the file systems with this.